Okay, so you're here with us because you want to get straight to the point, right?
Yeah.
No beating around the bush. You want the crucial stuff about what's happening right now.
Exactly. You want to cut through all that noise and get to the heart of the matter quickly.
That's what we do here.
Yeah.
So today we're diving deep into nuclear fusion energy.
It's been a topic of discussion for what feels like forever, doesn't it?
Yeah, it really has that clean, almost limitless power source, always just out of reach.
Tantalizingly close.
But recently it feels different, like something's shifted. The news has been so much more promising, and I think it's got people wondering what's actually going on and what does it all mean for the future.
And that's exactly what we're going to do today, isn't it? We're going to try and paint a clear picture of the recent advancements, the incredible potential that fusion holds, but also the very real challenges that still need to be tackled before it can become a widespread reality, right?
Absolutely. So we've been gathering a ton of information, the latest research and notes, up to March 2025. And our goal is to extract the crucial insights for you right now.
Distilling it down to what really matters.
Okay, so for decades, fusion has kind of been this mythical energy source, right? Clean, abundant fuel, almost too good to be true.
A bit like the holy grail of energy.
But it genuinely feels like things are changing. And the first major development that really jumps out from all our research is what happened at the Lawrence Livermore National Laboratory, LLNL, back in December 2022.
They achieved something called fusion ignition.
Now, for someone who's just catching up, what is fusion ignition and why is everyone making such a big fuss about it?
Well, what's truly significant about fusion ignition is this idea of energy balance, right? For years, fusion experiments were net energy consumers, so they actually required more energy to run than they produced.
Oh, right, so they weren't actually generating any usable energy.
Exactly. And fusion ignition is that pivotal moment when the energy released by the fusion reaction itself exceeds the energy that was initially put in to start it.
So it's like a tipping point.
Think of it like finally getting a roaring campfire going, where the wood itself sustains the flames after you've used a handful of kindling to get it started.
Okay, that's a really good analogy.
Yeah.
So this wasn't just some theoretical breakthrough.
No, not at all.
Yeah.
It actually validated the core physics and shifted the focus towards engineering the durability and efficiency of such reactions for continuous power.
Right, so this LLNL experiment in December 2022, could you walk us through exactly what they did?
Sure. So at LLNL, they used 192 incredibly powerful lasers, all focused onto a tiny pellet containing deuterium and tritium.
And remind us, what are deuterium and tritium again?
Right. So these are isotopes of hydrogen, basically later versions of hydrogen, which makes them more prone to fusing than heavier elements.
Okay, but it still takes an enormous amount of energy to actually make them fuse.
Oh, absolutely. We're talking immense temperatures and pressures.
So these lasers delivered 2.05 megajoules of energy to this tiny pellet.
That's right. And the resulting fusion reaction unleashed 3.15 megajoules.
So for the first time, we saw more energy coming out than was put in.
Precisely. And that's why it was such a huge deal.
More energy out than it. That's incredible. And here's where it gets even more interesting because it wasn't just a one-off fluke, was it? Our notes show they actually managed to repeat this.
Absolutely. The fact that they replicated this net energy gain in August 2023 was key.
So it showed that the initial success wasn't just a lucky coincidence.
Exactly. They could consistently achieve this result, which was a revolutionary step because it solidified the underlying science and made future, more predictable and efficient fusion reactions a real possibility.
Okay, so that's a massive leap forward using this laser-based approach.
Yeah.
But our sources also highlight progress on a completely different track over in China at the Experimental Advanced Superconducting Tokamak, or EAST.
A mouthful, isn't it?
It is, and it sounds like their focus was on keeping the fusion reaction going for a substantial amount of time at incredibly high temperatures.
Yes, you're right. While LLNL focused on that burst of energy gain, EAST achieved a new milestone and sustained high-temperature plasma.
Okay, so they were aiming for endurance rather than that sudden burst.
Exactly. In January 2025, they managed to maintain a plasma reaction at 100 million degrees Celsius, which is about 10 times hotter than the sun's core, for a remarkable 1.66 seconds.
Which is just shy of 18 minutes.
Yes, and that might not sound like a long time.
But at those mind-boggling temperatures, it's absolutely crucial for actually generating usable power over an extended period, right?
It is. You can't power homes and industries with a fusion reaction that only lasts for a tiny fraction of a second, no matter how much energy it momentarily releases.
So this achievement at EAST really demonstrates significant advancements in our ability to confine and control this incredibly hot plasma.
It shows that we're getting better at holding on to that energy and potentially harnessing it for practical use.
And what's really exciting is it's not just the big, well-funded government labs that are making waves.
That's right. The private sector is getting in on the action too.
Absolutely. Our deep dive uncovered some really intriguing innovation happening in the private sector, specifically with a company called OpenStar in New Zealand.
Now, their method is quite unconventional.
They're trying something completely different from the massive laser arrays or those huge, complex magnetic coils that we usually associate with fusion reactors.
They're experimenting with levitating a superconducting magnet directly inside the plasma itself.
Levitating a magnet within the plasma. It sounds like something straight out of science fiction.
Yeah.
What have they managed to achieve with this unique technique?
Well, they've successfully created plasma at a temperature of 300,000 degrees Celsius and sustained it for 20 seconds.
Okay, so the temperature is lower than what we saw at East, and the duration is shorter.
Yes. But the real significance here is the potential for a much simpler and cheaper reactor design.
Because they're not relying on those massive lasers or those complex magnetic coils.
Exactly. And this could be a real game changer in accelerating the commercialization of fusion by making it more accessible and less capital intensive.
So while the immediate numbers might not be as dramatic as some of the other breakthroughs, the simplicity of their approach could be more disruptive in the long run.
Potentially, yes, by lowering the barrier to entry.
So we're seeing these really exciting developments across different approaches. Net energy gains sustained high temperatures and innovative designs from the private sector, aiming for simplicity. It's hard not to feel a surge of optimism about the future of fusion energy, but let's step back for a moment. Why is there such a global push to make this work? What are the major advantages if we can actually master fusion power?
Well, the allure of fusion is really multifaceted, first and foremost. It's a source of clean energy, unlike burning fossil fuels. Fusion produces virtually no greenhouse gas emissions, making it an incredibly powerful tool in our efforts to combat climate change.
Right, and we all know how urgent that is.
Absolutely. Plus, it offers the potential for a consistent 2047 power supply, which is a major advantage over some other renewable energy sources like solar and wind that are inherently intermittent.
Okay, so that's huge. It's clean and it's reliable. What about the fuel itself? Our sources consistently emphasize that it's practically inexhaustible, which is a pretty compelling argument in itself.
It is the primary fuel sources for fusion are deuterium and tritium.
And we touched on this earlier, but just to remind everyone, where do we get those fuels from?
Well, deuterium is abundant in seawater and can be extracted relatively easily through hydrolysis.
So we're talking about a practically limitless supply there.
Exactly. And while tritium is rarer, it can be generated from lithium, which is also plentiful on Earth.
So that abundance means we're looking at a potential energy source that could literally last for millions of years.
A stark contrast to the finite nature of fossil fuels.
Okay, so it's clean. The fuel supply is essentially
Sources.
endless. What about safety? Because I think the word nuclear can sometimes raise concerns. So how does fusion compare to traditional nuclear fission in terms of safety and the waste it produces?
That's a really important point. Fusion is inherently much safer than nuclear fission. It doesn't produce the long-lived radioactive waste that fission reactors do, which requires storage for thousands of years.
So no need for those huge underground storage facilities.
Exactly. The primary byproduct of the fusion reaction is helium.
Helium, the stuff that makes balloons float.
That's the one. It's an inert and completely harmless gas. This makes fusion a far cleaner and safer option for both people and the planet in terms of waste disposal and the risk of uncontrolled chain reactions.
Right, because with fusion, if something goes wrong, the reaction just stops.
Exactly. It's not like fission where there's a risk of a runaway chain reaction.
That's a huge advantage. And our deep dive even hinted at another potential application that's a bit further down the road, space exploration. How could fusion technology play a role in our journeys beyond Earth?
Well, the potential for revolutionizing space exploration is truly exciting. Fusion propulsion could enable spacecraft to achieve continuous acceleration over long periods, allowing for much faster and deeper space travel.
So we're talking about significantly reducing travel times.
Yes, imagine a journey to Mars potentially being shortened from months to just weeks.
Wow, that would be incredible.
It could fundamentally change our ability to explore the solar system and beyond, opening up possibilities we can barely imagine right now.
Okay, so we've talked about the incredible promise of fusion clean, abundant fuel-enhanced safety, and even the potential for revolutionizing space travel. But we also need to be grounded in reality, and our sources outline some significant hurdles that still need to be overcome before fusion power becomes a widespread reality. Let's delve into those challenges. The first one that comes up is scaling up And seeing the complexity of that LLNL setup with its 192 lasers really underscores the challenge of making this technology more manageable and less like a massive scientific undertaking.
Yes, scaling up is a really significant challenge. Current fusion reactors, while achieving these impressive scientific milestones, are often enormous, incredibly complex, and correspondingly expensive to design, build, and operate.
So it's not exactly something you can just build in your backyard.
Not yet. The International Thermonuclear Experimental Reactor ITER, which is currently under construction, serves as a prime example of the sheer scale and cost involved in these large-scale research projects.
And then there's the issue of fuel, specifically tritium. We know deuterium is readily available, but tritium is not. We touched on the idea that it can be generated from lithium, but how does that practically impact the feasibility of fusion power?
You've hit on a critical point. While deuterium is abundant, tritium is scarce in nature, so future fusion reactors will very likely need to breed their own tritium.
So the reactor itself would create more tritium.
Exactly. This involves incorporating lithium into the reactor design, often as part of the reactor walls. When the high-energy neutrons produced during the fusion reaction collide with the lithium, they can transmute it into tritium.
So the reactor essentially becomes its own fuel factory for tritium.
In a way, yes, it's a very clever solution.
It is, but our notes also highlight some really significant challenges in material science.
Mm.
These reactors are dealing with unbelievable levels of heat and intense radiation. What kind of materials can even withstand those extreme conditions for extended periods?
This is a very active area of research currently. Tungsten is considered one of the most promising materials for the plasma-facing components of the reactor due to its exceptionally high melting point.
But even tungsten has its limitations, right?
It does. It can slowly erode under the intense conditions and contaminate the plasma, which then reduces the efficiency of the fusion reaction.
So scientists are looking for even better materials.
Absolutely. They're actively exploring and testing alternative materials like beryllium and even liquid lithium, which
Yeah.
might offer improved performance and greater longevity in these incredibly demanding environments.
And finally, we can't overlook the big question mark cost and commercialization. Even if we can get the fundamental science to work perfectly, if it's prohibitively expensive or impractical to deploy on a widespread scale, fusion will remain a fascinating scientific endeavor rather than a solution to our energy needs.
You're absolutely right. For fusion to truly become a widespread energy solution, we need to develop reactors that are significantly smaller, more efficient, and crucially much cheaper to build and operate.
Which is a huge engineering challenge.
It will require significant breakthroughs, not just in the core science, but also in engineering, advanced materials manufacturing, and overall industrial processes to bring the cost down and make fusion power economically viable and competitive with other existing and emerging energy sources.
It sounds like a monumental undertaking. But our sources also paint a picture of increasing global momentum and significant investment flowing into fusion research and development. So let's talk about the global landscape. Who are the major players in this race, and where is all this money coming from?
What's really encouraging is the substantial growth in investment we're seeing from both government initiatives and the rapidly expanding private sector. There's a palpable sense of a global push towards realizing commercial fusion power.
So governments and private companies are both betting big on fusion.
Exactly. And notably, private investment in fusion energy has surged dramatically in recent years, which really signals a growing confidence in the underlying technology and its future potential.
And it seems like there's a real sense of a competitive race unfolding globally, with the United States playing a particularly strong role, especially within that burgeoning private sector.
That's right. The U.S. has a very strong presence in the private fusion landscape. Our data indicates that a significant majority, around 25 out of the 40 companies that make up the Fusion Industry Association, are based in the United States.
So there's a lot of innovation happening in the U.S.
There is, and this dynamic private sector is widely seen as a critical driver in accelerating the timelines for commercialization, with these companies often pursuing innovative and sometimes riskier approaches than traditional large-scale government projects.
Okay, so now the question everyone wants to know, when are we actually going to see fusion power being fed into the electricity grid? Our deep dive touches on the projected timelines for some of these key projects.
Well, the projected timelines do vary, ITER, as a massive international collaborative endeavor has a revised goal of achieving first plasma by 2034 and full fusion by 2039.
So that's still quite a ways off.
It is, however, several private companies such as Commonwealth Fusion Systems and Helion Energy are considerably more optimistic, aiming to have functional pilot power plants online sometime in the 2030s, with some even suggesting the potential for connecting to the grid within the next decade.
So potentially within the next 10 years, we could see fusion power on the grid.
It's possible Commonwealth Fusion Systems' Spark project, for example, is aiming to demonstrate net positive energy as early as around 2027, which would be a truly significant milestone on the path to a commercial power plant.
Those are certainly ambitious but exciting timelines. It really does feel like the field is gaining serious momentum after decades of more incremental progress. Now, for those of us who want to understand the fundamental science a little bit better, can we break down the core principles of nuclear fusion in relatively simple terms?
Of course, at its heart, nuclear fusion is the process of forcing together light atomic nuclei, such as those of the hydrogen isotopes, deuterium and tritium, at incredibly high temperatures.
So basically smashing atoms together.
In a way, yes. When these nuclei overcome their natural repulsion and fuse together to form a heavier nucleus, which in this case is helium, a tiny amount of mass is converted into a truly tremendous amount of energy.
And this is the same process that powers our sun.
Precisely, it's the ultimate source of energy in our solar system.
And this fusion process happens in a specific state of matter called plasma, right? What exactly is plasma and why is it so crucial for achieving fusion?
Plasma is essentially a superheated ionized gas. Think of it like a gas where the atoms have been stripped of their electrons, creating a soup of charged particles. The extreme temperatures required for fusion, we're talking about tens to hundreds of millions of degrees Celsius, are what cause this ionization.
So it's like a super energized gas.
Exactly, and plasma is necessary because it allows the positively charged hydrogen nuclei to have enough kinetic energy to overcome their natural electrical repulsion and get close enough to fuse together.
And we actually see plasma in nature too.
We do lightning, and the aurora borealis are both naturally occurring examples of plasma, though at vastly different temperatures and densities than what's needed for fusion.
Okay, so finally our deep dive mentions different confinement methods for this incredibly hot plasma we've already heard about, tokamaks, and what LLNL accomplished with lasers. Can you briefly explain these two primary approaches?
Absolutely. The two main strategies for confining and controlling this incredibly hot plasma are magnetic confinement and inertial confinement tokamaks, like the East facility and the planned ITER, utilize powerful magnetic fields generated by superconducting coils, or even by the plasma itself, to contain the plasma within a donut-shaped vacuum chamber.
So the magnetic fields essentially act as an invisible cage.
They prevent the charged plasma particles from colliding with the reactor walls, which would cause them to cool down and halt the fusion reaction.
Okay, and inertial confinement, that's the method used by LLNL with those powerful lasers, right?
Exactly. It involves using those lasers to rapidly compress and implode a tiny pellet of fuel, creating the necessary conditions of extreme pressure and temperature for fusion to occur in a very brief but intense burst.
So two very different approaches, but both aiming for the same goal.
That's right, controlled nuclear fusion.
So to summarize, we've seen remarkable progress using both magnetic and inertial confinement techniques. It really feels like the decades of dedicated research are finally starting to pay off.
It truly does. The combination of these recent breakthroughs, the immense potential benefits that fusion offers, and the increasing levels of global investment all strongly suggest a field that is rapidly maturing and moving closer to practical application.
So it's no longer just a pipe dream.
Not at all. While significant challenges undoubtedly remain in scaling up the technology, ensuring a sustainable fuel supply, mastering the complexities of material science, and ultimately driving down the cost, the sheer level of innovation and the pressing global need for clean and sustainable energy solutions are powerfully driving the boundaries of what's scientifically and technologically possible.
And what's really exciting is that it's no longer solely the realm of traditional government-funded research institutions. The private sector is playing an increasingly vital role.
Precisely, the healthy competition and the diverse array of innovative approaches being actively explored by private companies are absolutely crucial in accelerating the overall development and eventual commercialization of fusion power. These companies are often more nimble and willing to pursue unconventional designs and take calculated risks, which could ultimately lead to crucial breakthroughs that nicely complement the ongoing efforts of the larger publicly funded projects.
Well, this deep dive has been incredibly insightful and genuinely feels like we've moved beyond simply discussing the theoretical promise of fusion and are now witnessing tangible, exciting progress towards making it a reality.
I agree. We're seeing a powerful convergence of fundamental scientific validation and rapid technological innovation that strongly indicates fusion power is no longer a distant aspiration, but a tangible goal that could be within our reach in the coming decades.
So as we bring this deep dive to a close, let's leave you, our listener, with a final thought. To consider even acknowledging the inevitable complexities and hurdles involved in the initial deployment of such a revolutionary technology. How could the widespread realization of commercial fusion power fundamentally reshape not just our global energy systems and our relationship with our planet, but also our ambitions for exploration and our reach in the vast expanse of space? It's a future that is certainly worth contemplating deeply. Thanks for joining us on this deep dive.
It's been a pleasure.
And we'll see you next time.
Until then, bye.